Thanks a lot.
Okay, great. Thank you, Gerhard. And my presentation will switch a bit of gears. So from the biology of lipids and pathway to the methods of how we can analyze them. And I would like to mention from the very beginning that my talk will be really basic and meant to be just a general introduction into LC-MS-based lipidomics, because after my talk we will have the whole series for today and tomorrow excellent presentations which will introduce you much more deeply in how we can analyze lipids and lipidomes in general using mass spectrometry. So for some of you who are dealing with mass spectrometry already, that might be too basic, but just to set a stage for every one of us here, let's have a look how we can do mass spectrometry-based lipidomics. So lipidomics, as Valerie defined already yesterday, stands for a large-scale study of lipids, so diversified molecular species of lipids, to address their identification, cellular and tissue distribution, as well as to understand their signaling and metabolic pathways. So what kind of information do we usually get from mass spectrometry-based lipidomics experiments? So in principle, no matter what experiment we are doing, we could classify it into several very straightforward questions for which we want to get the answers. So very often we would like to know which lipids are present in my samples. So we want to perform identification of our lipidomes. Or we want to know what is actually the difference between sample A and sample B, and maybe we want to know how much more of certain lipid we have in a sample A relative to sample B. So in this case, we want to perform relative quantification of our lipidomes. And finally, we might want to know what are exactly the concentrations of all detectable lipids in our samples, and what is the concentration of specific predefined set of lipids in a sample A and B. So we want to make maybe absolute quantification. And I believe that majority of the studies we are performing using mass spectrometry-based lipidomics can be classified to answer one of those three basic questions. So how we can do that? Every lipidomic experiment which involves mass spectrometry-based lipidomics start always with sample preparation, so we can extract lipids from the variety of different matrices using different kind of methods. We perform mass spectrometry experiment with or without chromatography. And afterwards, we go on with data analysis, as all omics technology provides us a very big set of data, and we usually would need different software tools nowadays in order to process these very complex lipidomics data sets. But let's focus now on that part about LC-MS-based technology here. And the key component or instrumentation in all of those experiments is mass spectrometry itself. So mass spectrometer consists of different components, and of course the main one which we have in the mass analyzer, which allows us to separate ions of our analytes, lipids in our case, based on their mass to charge ratio. And the key words here is probably ions, because we perform this event of mass analysis or separation based on their mass to charge ratio by manipulating ion behavior in electric or magnetic fields. So we can perform our mass analysis only if we manipulate ions, as obviously only they will respond to this electric and magnetic field. So if we have to manipulate ions here, it implies that we have to ionize our analytes. That's why a very important part of any mass spectrometer is also an ion source, where we form ions from molecules, from neutral molecules. And usually we want to do that without some decomposition and additional fragmentation events. So these ionized lipids can be separated based on their mass to charge ratio in electrical magnetic fields of our mass analyzers. And at the end, we can detect either ion count or image charge or current depending on the mass analyzer you are using. So we have to ionize, separate, and detect. So the problem in lipidomics is that a very high number of lipid molecular species are actually occupying a relatively narrow mass to charge space. We will see later on that lipids are ionized usually as a singly charged molecules, majority of them. So if we talk about this 40,000 of lipid species, which we think are out there, they all will be distributed in MOZ range around 1000 MOZ values. So this is a very densely populated MOZ space, and that of course reflects this high diversity of natural lipidomes, this high number of isomeric and isobaric species, and can result in certain ion suppression events. And also, of course, ionization of lipids will depend on their chemical properties, so they might also compete for the charge. Just to illustrate you how many different isomeric and isobaric species there can be, here you could see the plots where we have exact mass of certain lipids, different lipid categories and subclasses are shown in different colors, and a number of isomeric species on the y-axis. So around 760 in this region, we can have with you more than 40 different isomeric, isobaric species within 5 ppm mass accuracy. And if we move to the glycerol lipids, like triacylglyceride regions, we can have with you more than 60 different isomers and isobars. So that's why very often we combine mass spectrometry separation with chromatography separation in front of that. We can do that, or we can also do not do that, because, and Gerhard, I guess, will show you in the talk next after me, how you can do mass spectrometry-based lipidomics without the separation, but sometimes we do from LC-based separation before. So the separation using chromatography techniques is usually, it's based on lipid physical chemical properties. And here we made just kind of illustrative exercise to see how this physical chemical properties described by 26 molecular descriptors can actually classify or cluster different lipids. So we took from the database around 23,000 lipid structures and calculated for them 26 molecular descriptors for each of those ones, and then perform principal component analysis to see how they will be distributed. So it's, I don't have to look much into the details here, but just have a look that each of the lipid categories and class is colored here with different colors. And you can see that, of course, different groups of lipids, classes of lipids, they cluster together. And their behavior can be described by these two main principal components. And if we look which kind of these molecular descriptors actually defining their behavior, it becomes very logical that in the principal component 1, where we have a separation of lipids within one category, for instance, these black ones or these violet ones, the main separator is, for instance, the polar hydrophobicity, defined by log p values. Wherever in the principal component 2, we have the main influence of polarities. And that actually perfectly fits to the two main chromatography methods which are used in the lipidomics, when we separate, for instance, our lipids based on their hydrophobicity using reverse phase chromatography, or in the other way, we can separate our lipids based on their polarities. So in this case, we separate different classes of lipids using normal phase chromatography, or which is more commonly used nowadays, a hydrophilic interaction chromatography. So indeed, those two methods are the most popular ones. And again, I'm not going into details because Michal Holzapek will be talking about chromatography, and he's really an excellent expert in the chromatography techniques for lipidomics, just to give you a brief idea about reverse phase chromatography, so where separation is based on partitioning and analyte hydrophobicity. So we have these different types of stationary phases where silica particles are functionalized with usually hydrophobic ligands. So for sure you heard something about C18, C8, C30 chromatography columns. Or we can, and then we have a mobile phases which are polar and made up from water and water mixable organic solvents. So the retention is based on our lipid. Yeah? So you could see it here. The lipid is retained on the column based on its unpolar parts, fatty acid chains here due to the hydrophobic effect, and we can elute it with increasing percent of organic solvent. So on the other hand side, we can have our hydrophilic interaction chromatography, where we have our orthogonal mode of separation based on lipid polarities. So now the other part of our lipid molecule come in play here, the one which is characterized by the so the head groups, for instance, of phospholipid. We have a stationary phases based on silica, and they can be neutral, charged, and switterionic. And our mobile phase is water and water mixable organic solvent as well. So, and also important for Helix to have always some percent of water to form this aqueous film on the stationary phase. Retention is really a complex mechanism here, and it's really multimodal, and we elute here with increasing percent of water, leading to the disturbing this interaction of our polar head groups and the stationary phase. So one way or another, we can separate our lipids. So as we just talked about here, either based on their hydrophobicity, so using the property of their fatty acyl chains, or their polarities based on the head groups, so different classes. So the next step would be is to ionize, right, our lipids before we can perform our mass separation events in our mass analyzers. So the most popular ionization methods in lipidomics are electrospray ionization and matrix-assisted laser desorption ionization. Both of those two are soft ionization methods, so they allow us to bring our lipid analyte in the gaseous phase and ionized form without extensive decomposition. But there are also other techniques like atmospheric pressure chemical ionization or electron impact ionization still used for certain particular cases. And when you decide how to ionize your sample, which kind of ionization methods to use, so you usually would compare, so think about the polarity of your analyte. So if your analyte is very unpolar, then electron impact and APCR might be methods of choice, but only for the lower molecular weight analytes. And when you move to the higher molecular weights and analytes with a higher polarity, so we go for electrospray and multi. I will not talk about each ionization technique here, of course, just briefly mention that electrospray by no means the most popular method of ionization nowadays, because it is relatively soft. You can modify the ionization process and actually direct it by using the solvent chemistries, and you can couple it to the liquid chromatography as well, which provides you this orthogonal LC-MS dimensions. So in the electrospray ionization, our analyte solution is present already as ionic form in the liquid, and we perform, so we apply the voltage between the capillary and the entrance to the mass spectrometer in such a way that, let's say here on this cartoon shown, positively charged ion will be directed and dragged towards the mass spectrometer entrance. And for the small molecules, small analytes as our lipids, it's usually postulated that the ionization process happens by the ion evaporation model, when from those big droplets, the ion pop out and directed further to the entrance of a mass instrument. So if you are interested in reading more about that, so I always put some literature here, which you can check out afterwards. Okay, so how that actually ionization happens. So what do we need to have in our solvent here to help our lipids to form positive or negative ions? So we always have to look to the chemistry of our solvent or mobile phase, and usually we would add acids or volatile salts such as ammonium formate or acetate, or in terms of acid corresponding formic and acetic acid to help this ionization process. So very popular combination is, for instance, to add low concentrated ammonium formate and some amount of formic acid inside. And just to illustrate you what really happens here. So for instance, we have here our neutral glycerol-phosphatidylcholine lipid. Yeah, so that's all chains and glycerol, and we have a phosphate group, and we have our choline moiety, and total net charge of this lipid is 0, but we have here negatively charged phosphate group, and we have a positively charged trimethylamine group here. So if we want to bring this lipid in ionized state, so we can do it either in positive or negative mode. So if we use a positive ion mode ionization, we would add a proton here, so we will have a positive charge retained on the head group, and the negative charge is neutralized, so we can get a positively charged ion. Or whatever happens in the negative ion mode, we can actually block this positive charge by the non-covalent adduct with a formate and ion, and in this case, so this positive charge is blocked, and we have with you a negatively charged ion of phosphatidylcholine lipid. So, and using this chemistry in solution of different combination of ammonium, also different salts, volatile salts or acids, so we can induce ionization of different lipid classes. So logically, after ionization, we finally ready to analyze or separate our ions using mass spectrometry or mass analyzers. And of course, here we have a wide choice how we can do that. So nowadays we have a really whole panel of different mass analyzers available. So quadrupole, ion traps, time of flight, orbit trap, Fourier transform ion cyclotron resonance. So for instance, in the ion quadrupole, which I show you here, we can separate our ions based on their mass to charge ratios by manipulating electrodynamic field, which we form between these within these four rods in such a way that at one moment of a time, so at one settings of this electrodynamic field here, only one mass to charge ratio ions will have a stable trajectory and pass to the detector, and the other will hit the walls and we will not see it. But we can swap these settings so fast that we can let ions one by one go through. So, for instance, another type of mass analyzer, time of flight, here it's completely different principle. So here we actually accelerate our ions before they enter field-free drift zone, and the ions will fly to the detector. So, and we will measure the time it will take them to reach the detector with all the settings the same. The time it will take depends on the mass of those mass to charge of those ions. And again, I do not go much into the details here, but just to give you a brief idea that the principle of separation operates different. So based on the principle of how this mass analyzer are designed, we have, of course, different characteristics, which we usually would charge before we decide to use one or another type of mass spectrometer for the experiments we want to perform. So very important characteristic is a resolution and mass accuracy of our instruments. So some of them are low resolving instruments, but some of them are very high resolving based on the principle how they operate. The other important parameter is, of course, a speed, how fast we can perform this one mass analysis event where we can analyze all ions present, ionized in the moment, or some selected ones, and also how this one mass to charge separation event actually happens. So in the scanning mode or in the screening mode, like I showed you here with the quadrupole cell. We let ions one by one go through, so we're kind of sequentially separated. And such a mass analyzer like time of flight and orbit trap, for instance, we have simultaneously acquires a full mass to charge range. So if you're thinking about design of your experiments, you usually would consider those facts. So when finally we decided how to separate, ionize, and mass analyze our ions, we can get with you the mass spectrum, which can look like that. So it's a negative electrospray ionization mode, and the spectrum is acquired in the orbit trap mass spectrometer, which is highly resolving one. So we see certain ions, mass to charge ratios of certain ions, and as I told you, if we do it in the high resolution and high mass accuracy mode, from this mass to charge ratio we can actually deduce already the elemental composition of our analyte. So if we have an elemental composition, we can already think about that, okay, that might be our phosphatidylcholine lipid, which we looked with you during the ionization event before as a formating duct. But can we really say, that we identify lipid here? No. So everything what we have this elemental composition of this analyte within certain mass accuracy ranges, for instance, 3 ppm, something like that. But we don't have any idea, is it this kind of phosphatidylcholine with 16,0,20 to 4 combination of acyl chains, as is on the picture, or maybe it is PC lipid with 2 alleic acid or something else at all. So that means we have to do with you a next kind of mass spectrometry based experiment, which is usually called a tandem mass spectrometry, which we will use for lipid identification. So we want to select this specific ion. We want to fragment this specific ion, which will break this ion apart into some set of specific fragments, which we measure again, so we separate again, and that will allow us to distinguish what kind of lipid we actually have in this case. So here we need to work now with a hybrid mass spectrometers, which will have a set of mass analyzers. So because one we will use for the selection, and the second one we will use to measure and detect fragment ions. So we also need another device in between, which we call a collision cell, where we can collide our activated precursor ions with a neutral gas. And in these collision events, the activated precursor ion will fall in the parts, so forming these fragment ions, which exactly we want to have in order to find out what kind of lipid do we have in our samples. So if we now do our tandem mass spectrometry experiment, so first we measured our MS scan, we see our precursor of interest, we would like to know exactly what is that. So we would select it and fragment it and record the fragment spectrum. So here I show you an example of 2 fragment spectra, each of them obtained from the precursor with exactly the same mass to charge ratio. You can see that we have some set of fragments which are exactly the same in between scan 1 and scan 2, but we also have fragments which are quite different. So here, I am not going now into the identification, you will see that later as well. But using the set of fragments, so the ones which are the same tells us, okay, both of those are phosphatidylcholine, but the ones which are the different ones, they tell us these 2 phosphatidylcholine lipids, they actually have a different fatty acyl composition. So that upper one has 2 linoleic acid and the down one has, for instance, palmitic and arachidonic acid here. And if we look further on the retention time of those 2 signals, we can also see that in our chromatography, we also have a nice separation of those 2 isomeric lipids, but using this tandem mass spectrometry experiment, we can define the composition of their acyl chains. So if we go for lipid identification, we always have to work with 2 mass spectrometry experiments. Here, MS1 or full MS scan, where we look for the precursor mass to charge ratio, we can define elemental composition. And for instance, if we have with you a hybrid mass spectrometer, which consists of a quadrupole collision cell at time of flight, we can just let quadrupole to pass all ions through. Collision cell is not active, so we record all our precursor M over Z in the time of flight. If we want now to switch to the second type of experiment, so Tandem mass spectrometry experiment, which we need to find the specific fragments for identification, we now use quadrupole to select this ion of interest. Collision cell will perform this fragmentation event and record the fragment spectra in the second mass analyzer. So by combining this MS1 and this MS-MS or Tandem mass spectrometry experiments, we can always see our precursor ions and then select the ones which we are interested for the fragmentation event. We can do it with other type of hybrid instruments, for instance, with a quadrupole and orbit trap combinations. So, and usually we would select here as a second mass analyzer something with a high resolution to get a very accurate mass to charge ratios. Of course, that is very logical, but we would not sit in front of the mass spectrometer ourselves and say, okay, now this, select this and this and this. Yeah, so that's not a high throughput lipidomics if we would have to select every precursor ourselves. So we have to design methods which will allow to do it automatically. And one of the most popular way of doing that for untargeted lipidomics is the so-called data-dependent acquisition. So for that, this untargeted method, we exactly do like I described you, yeah, but our computer embedded in the mass spectrometer programmed in the way that from each MS scan, it will select several most intensive precursors, which will undergo this fragmentation and separation of fragment ions. So one cycle of our method here will include one MS scan and several MS-MS scans in order to get the information as a fragment ions for our precursors. So the good thing about that it goes really automatically and fast. So we collect with you, for instance, for 30 minutes LC-MS run, more than 1,500 unique MS-MS scans, which provide us this large coverage for lipid identification without any prior knowledge of the sample. So there is not much we have to think about before. And since we are selecting these abundant precursors, usually our spectra have pretty good quality. Yeah? So the more intense ion we are selected, the more intense fragment ions we get. So, and then we can have an accurate identification. But on the other hand side, that is also exactly the problem for this method, because this method is biased towards highly abundant analytes and results in what we call undersampling. So the low abundant analytes are not so good represented and not reproducible. So it cannot trigger MS-MS scans, and that means not identify all analytes. And we also need to think that in this method, we go usually for the high identification coverage. So we want to have a lot of MS2 scans. So it's not really perfect for quantification purposes. So what has now become more and more popular, a second solution for untargeted lipidomics is so-called data, sorry, there is a mistake here. So it's data-independent acquisition. So this is a method which allows us actually to obtain spectra truly for all ionizable analytes. And there are two versions of those methods available now. One is called all ion fragmentation, or MS to the E, and the second type is called SWAS, sequential window acquisition for all theoretical mass spectra. But the idea here is that we do not select any precursor based on the abundance, but we just fragment everything. So in case, for instance, of all ion fragmentation, the cycle consists now just from one MS scan and one MS2 scan. Instead of selecting something for the fragmentation, we just let all ions through our quadrupole and all of them are collided in a collision cell. So indeed, we actually fragment every single ionizable ion in using like this whole window or the smaller window in SWAS, which is truly untargeted method, and we get fragment spectra for all ionizable analytes. And in case of, for instance, all ion fragmentation or MS to the E, this method is also good for quantification. But the problem here is that we get with you a very mixed MS2 spectra. Yeah? So you see that here we have a fragment ions from very different precursors. Here, less complex, but still mixed. So there is no direct connection between our precursor and corresponding fragment ions. That's why in order to get the identification afterwards, we have to go through quite complex data process. So these methods are only now coming more and more popular in the lipidomics field, and more software solutions are becoming available to perform this complex data processing. So I believe in our tutorial session, at least one software, MS Dial, will be introduced, which can deal with this complexity of the multi-mixed spectrum. So finally, if we do not want actually to identify everything what we have in the sample, but we have already with you a pretty clear idea of what exactly we want to measure. So in this case, we can go for another type of mass spectrometry-based experiments, which are called targeted lipidomics. And one of the most popular methods here is multiple reaction monitoring. So in this method, our instrument works in such a way that we do not perform any MS1 scans. We only work with MSMS, so MS2 scans, because we define already specific precursor ions, which are selected here by the first quadrupole, fragmented in the second, and we also define a specific fragment ion. So we know everything about our analyte, and we tell our mass spectrometer to be super specific exactly for this kind of what we call transition. So the predefined precursor and predefined fragment ions. So the one cycle event here consists of several MSMS scans, depending on how many predefined analytes we have in our list. Yeah, how many of these precursor to fragment transitions we provided to our mass spectrometer to be measured. So the good thing about this method, this is fully targeted. That means all settings we are optimizing for this predefined set of precursor and fragment ions. That provides us a very good sensitivity. So this targeted lipidomics methods, they are by far more sensitive than any untargeted one. And since we also know this combination between precursor and fragment, and often we can provide also the retention time, so those methods also provide a high specificity. These methods are usually very good for quantification and also including low abundant analytes, because again, we are very targeted, we can be very sensitive. But other cons here, we can name that, of course, this is targeted method and we get information only about predefined set of analytes. And if we want to optimize the settings of our mass spectrometer for those predefined lipids in absolutely perfect manner, so we usually would need chemically defined standards to work with for this optimization, which sometimes might be not so easy to obtain. I would like to mention that nowadays there are another two targeted setups which become popular as well. So not only the triple quadrupole instruments, but also so-called top MRM, where we again select our specific precursor with a quadrupole, fragmented, but measure all fragment spectra in the time of flight mass analyzer, or parallel reaction monitoring, which is usually done on the Q orbit trap instruments again. So the quadrupole will select, collision cell will fragment, and the orbit trap will resolve and measure all our fragment types. So multiple reaction monitoring, TOF MRM, parallel reaction monitoring, the cycle time is always consistent on several MS2 events depending on the number of predefined analytes we are looking for. So to conclude here, I would like to summarize what I showed you as really introduction here, and many other speakers will go in much more details, but we can do our lipidomics in either untargeted or targeted manner. So if we go for untargeted lipidomics, usually our aim is to identify as many analytes as possible, preferentially all of them, including previously the ones which we had no idea. So it's like a discovery approach. Wherever in the targeted lipidomics, we usually want to quantify a predefined set of known analytes. So here we mostly go for identification, also quantification is also possible under certain conditions. And in targeted lipidomics, we usually go for quantification. It can be also used for identification in certain ways, but it's again a secondary process. And I provided you a very brief overview about main methods which we use for that. So data dependent, data independent acquisitions in different ways, or also targeted approaches such as MRM on the triple quadrupole, STOF MRM, or parallel reaction monitoring. Okay, with that, I will stop here, and I hope I gave you some very brief idea how things can work for LC-MS-based lipidomics.